Okay, students, in this presentation, we'll discuss one more important topics in data structure, that is graphs. In this small presentation, we'll see the terminologies used, various terminologies used. The first recorded evidence of the use of graphs dates back to 1736 when Euler used to solve a classical problem called Königsberg Bridge problem. You can see here there are some island places and these are all connected through the bridge. The river, that is Fregel River, flows around these islands. I'll enlarge the diagram. This is that. They're all the island places. This one, this one, this one, this one, this one. So this is Fregel River bridge connecting these islands. To solve that one, the problem is that starting from a particular place, the man or the person has to reach all the places and has to come back to the same place. But many of the mathematicians tried this one, but unfortunately, no one got the result. So this is the classical problem which uses the graph. Okay, this has seven bridges labeled A, B, C, D, E, F, and the island place A, B, C, D. Four land areas are given in the uppercase and the bridges are mentioned in the lowercase letters. The same problem is represented with the help of graph to solve that. This is how the problem is represented. A, B, C, D, and these are all the land areas. These are all the bridges, and A, B, C, D are the land areas. Others are the A, B, C, D are the land areas, and these connecting are the bridges connecting these land areas A, B, C, D. Now, how this problem can be solved? Starting from a place, so I'll be starting from C, moving towards B. So I'm taking this bridge to reach this one. After that, I'll come back to C from B, then to D, from D to B, B to A to D. You can see, you should not repeat, you should not use the same edge again. Even so, the one of that bridge is missing. You can cover up to 6 bridge only, not 7. You cannot come back. So you can try all different alternatives, but one will be missing. So to solve that one later, mathematician added one more edge connecting A and T. Connecting A and T. With this, we see whether we can reach all the points. Starting from C. Starting from C, traverse to B, from B to C, from B going back to C, C to D, then D to A to D, D to B, B to A to B. We cannot come back to C, but we can cover all the edges. We have solved, we have reached all the points. One thing is that one more bridge you have to construct from land A and B so that we can traverse all the bridges, we can reach, we can visit all the land areas. This is the preliminary solutions obtained. Starting from B, here the land areas are indicated with letters uppercase A, B, C, D, and lowercase indicates the bridges A, B, C, D, E, F, and all the bridges connecting those land areas. Starting from the land area B, starting area, land area from B travels to A through bridge A. From A travels to D, then to C, then to C. First is from B to A, then through E to D, through G to C, through D back to A, from B to this land area B, through F to D. You can see one more edge is missing. We can traverse in all the bridges, we can reach all the land areas, but we cannot cover one of the bridge. Now we'll start the ideas behind in this graph. Graph G, you take any graph, this is a graph. Graph G consists of two things. One is non-empty vertices. This is vertices. 0 and 1 are the vertices. They cannot be empty. When vertice is not there, you should not represent. You have got only two vertices. Those are the part of the graph. That is the vertex list. And a possibly empty set of edges. For example, this is my nodes. This is my nodes. This is also graph. This is 1, this is 2, this is 3. This is a graph. 1, 2, 3 are the vertices, but edges are not there, empty edges. This is also a graph. 1, 2, 3 are the vertices. There is an edge from 1 to 2 or to 1, but there is no edge from 1 to 3 or 3 to 2. Okay, we can have empty set of edges, but vertices cannot be empty. These are indicated with respect to graph. V of G represent vertices, E of G represent set of edges. So we can also represent a graph. For example, if I say this is a graph G, then it has vertices and edges. So this is represented. This is represented for the graph. So in this case, G is, what are the different vertices? V, E. With reference to this small graph, what are the list of vertices? List of vertices are 0, 1. 0 is vertices and 1, vertices. And what are the edges? The list of edges, set of edges are 1 is 0, 1, 0, 1, it is one edge. The other one is 1, 0, 1, 0. Why? Because we can traverse from 0 to 1 or we can traverse to 0. This type of graph is called undirected graph. There is no direction. I will tell you one more example. This is a graph. I will indicate this here. G, number of vertices and edges. It has got two vertices, 0 and 1. One edge from 0 to 1. The list of edges E, list of vertices V. So V list number of vertices are 0, 1. Number of edges are, as it is a directed graph, 0, 1 is the only one edge. It's connecting from 0 to 1. It is a directed graph. A directed graph is one in which we represent each edge as directed pair of vertices. Here there is an edge connecting from 0 to 1. There is an edge connecting from 1 to 0. So vertices V0 and V1 are the vertices. V0 and V1 is connecting and V1 and V2 are connecting. This is the thing. V0 and V1 are connecting. V1 and V0 are connecting. The list of vertices are V0 and V1. So this is an example for direct graph because there is a direction which connects from where to where. A complete graph is a graph that has maximum number of edges. For an undirected graph with n vertices, the maximum number of edges is the number of distinct unordered pairs Vi and Vj. Vi and Vj. The number is given by n into n minus 1 divided by 2. But in case of directed graph, for the complete graph, the maximum number of edges is n into n minus 1. Now we'll take this example. There are four vertices 0, 1, 2, and 3. 0, 1 is connected. Only once you have to consider. 1 to 0 is not necessary. Consider. So the number of edges in this case 1, 2, 3, 4, 5, and 6, and number of vertices 4. So maximum number of edges given by 4 into, that is n into n minus 1, 4 into 3 divided by 2. 4 into 3 is 12, divided by 2 is 6. You can see there are 6 edges. This is an example for undirected completely connected graph. All the edges are connected. All the vertices connected to all the other vertices. 0 is connected to 1, 2, 3. 1 is connected to 2, 3, 1, 0. 2 is connected to 0, 1, 3. 3 is connected to 1, 2, 0. All vertices connection to all other vertices. The relation is 4 number of vertices into 4 minus 1, that is 3. 4 into 3 is 12 divided by 2. Half of that is 6. This is for undirected graph. In case of directed graph, as you can see, there is a path from 0 to 1. Also, there is a path from 0 to 1, 1 to 0. In the same way, 1 to 3, 3 to 1. These are all unique path, 0 to 1 and 1 to 0. Like when you start from Bangalore, reaching Bangalore is one of possibility. In the same way, you can start from Bangalore, you can also reach to Bangalore. So these are entirely different. The direction is different. Here direction is added. This type of graph is called completely connected directed graph. In this case, all these are unique edges 0 to 1, 1 to 0, 1 to 2, 2 to 1, 0 to 3, 3 to 0, 0 to 2, 2 to 0, 2 to 3, 3 to 2, 3 to 1, 1 to 3 are all the connected graph, connected edges. The number of vertices 3, number of vertices 4, 4 into 3 is 12. You can see there are 12 edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n into n minus 1 in case of directed connected completely connected graph, n into n minus 1 divided by 2 is case of undirected completely connected graph. We'll see some examples. This is completely connected graph, but it is undirected. Graph G1 is graph. This G1 is completely connected undirected graph. This is a tree. In the first example, that is in G1, there is no hierarchical. All are connected, those are not hierarchical. This is a graph, but it is also called tree because it is in the form of hierarchical order. There is a parent-child relationship. 0 is a parent and 1 and 2 are the children of 0. 3 and 4 are the children of 1. 5 and 6 are the children of 2. This is a tree, a special type of graph where there is a hierarchical order. But here there is no hierarchical order. There is a path from 0 to 1 as well as 1 to 0. This is also a graph. This is also a graph. It is not completely connected graph because there is no connection from 2 to 0 directly or 0 to 2 directly, but there is a direction. 0 to 1 there is a path, 1 to 0 there is a path, 1 to 2 is a path. You can represent that in this way. The list of vertices 0, 1, 2, 3 are the vertices in this graph 1. Number of edges 0 to 1, 0 to 2, 0 to 3, 1 to 2, 1 to 3 and 2 to 3. In case of tree, the vertices are 0, 1, 2, 3, 4, 5, 6. The edges are 0 to 1, 0 to 2, 1 to 3, 1 to 4, 2 to 5 and 2 to 6. In the last example, graph G3, the vertices are 0, 1, 2 and what is the 0 to and edges are 0 to 1, 1 to 0 because arrow towards 0 and arrow towards 1 and other one is 1 to 2. Okay, but in case of undirected graph, you can write this 0 1 in 1 0 form also because there is no direction. You can write this in alternate way, these two in alternate way, but you cannot write this in other way. Only if arrow is there, then you cannot write. Starting point towards the arrow point. Starting point is 0 and towards 1. That is the representation in case of directed graph. If V0, V1 is an edge, you take any graph, V0, V1 is the edge in an undirected graph. This is undirected graph. Then vertices V1 and V2 are the adjacent. We can say 0 is connected to 1, 0 is also connected to 2. That is why 1 and 2 are the adjacent for A, adjacent for 0. In this example, if V0 and V1 are the two vertices and there is an edge in the undirected graph, V0, V1 are the two vertices and there is an edge connecting V0 and V1, then this V0 and V1 are the adjacent. This edge is called incident. You can say this is incident, this is incident, this is incident. Okay, so for if you take one, the node 1 and node 1 is connected to 0 and the node 1 is also connected to 3 and 4. For 1, 0, 3, 4 are neighbors, also called adjacent. 1 for 1 no, 0, 3, 4 are the neighbors or adjacent. And for 1 incident, in this node incident, this is the incident on node 1 to 0. If V0 V1 is a directed edge, then V0 is adjacent to vertex V1, while V1 is adjacent to V0 in case of directed graph. Here, uh, V0 and V1 are the incident, these two are the incident, and 0 to 1, 1 to 0, 1 to are the incident kind of thing. 1 and 0 are the accident, this is incident, this is incident, this is incident. Subgraph. This is if you take this graph, a part of that graph, a subset of all those are considered as graph. A graph vertices, okay, part. This is there in the main graph. You take that main graph in this way, connected. All these nodes are connected on that graph. 0 is here, is a subset, and if you can take 0, 1, 2, that's also there, 1, 2, 3 also there, and this are all the subset of subgraph of this graph. Okay, and if you consider this graph, they're all the subset or the subgraph of this graph. Okay, this is the main graph, they're all the part of this graph. A graph may not have an edge from vertex I back to itself, like here. There is no edge here, but it is connected to itself. This type of graph is called loop. Like there is an edge starting from 1 and set 1 null. Starting from 0 and set to 0. This is why this graph is an example for loop. This graph is an example for loop. But here there is a special type. There is a connection from 1 to 3 and 3 to 1. The same way 2 to 3 there are 3 edges. This graph is called multi-graph. This graph is a multi-graph. What I can say, if you start from a particular stop and you want to reach to other part, these are the alternate roads that are connecting from this place to this one. Alternate roads. Each road time may be less, cost may be less, road quality may be different like that. So all these are represented with this unique edges. That is why this is multi-graph. Multi-graph. This is the loop. This is multi-graph. A path from vertex VP to VQ in a graph is a sequence of vertices VP, V1, like that. These two are the starting point, all these are all the edges. If direct graph, then the path consists of these are all the paths. In case of so VP, VI1 and VI1 VP are entirely different, but in case of undirected, you can write it different way. A connected component or simply component of an undirected graph is a maximum connected subgraph. For example, if G3 has two components H1 H2, a tree is graph is connected and it's acyclic. There is no cycle here in case of graph. In case of tree, parent to child node only. There is no connection from child node to parent, but here you can have. Now, degree of the graph. We know how to compute the degree of the tree. Now we'll see how to compute the degree of the tree. If you take node 0, there are some vertices which originate from 0 towards other node. In the same way, there are some edges which comes to returns to that node. So this is the outer degree, this is the in degree. So degree of that zero is the sum of in degree and the outer degree. Okay, so outer degree is 1, in degree is 1, degree of 0 is 2. If you take this node in degree, there is only one incoming node, incoming edge is 1 in degree plus 2 outer degree, 1 towards 0, 1 towards 2, 1 plus 2, that is 3. That is degree of 1 is 3. For 2, only one in degree is there, there is no out degree. Degree of this 2 is 1, this is 2, and this is 2. The sum of in degree and out degree is the degree of the graph. If you take this example, degree of this, there is no in and out, but there are two edges. The degree of this node is 0, degree of this node is 3, degree of this node is, if you consider this as a graph, degree of this is 3 because two node, one is incoming, you can say like that. If di is the degree of the vertex I in the graph, then with n vertices e edges, then the number of edges is equal to sum of degree divided by 2. What different operations we can perform? One is you can create the graph, it returns graph. In the set of graph, V1 is all the vertices and this is V1, V are all the vertices. Okay, you can add a new vertex to the graph. This V is getting added, graph is going to change, so graph you are going to return. You can also edge, you can also insert an edge. For example, right now the graph is not there, empty graph is created. The operation is creating empty graph. Now I will be adding three vertices V1, V2, V3 are added. I'll be calling the routine insert vertex V1 for the graph, insert vertex V2 to the graph, insert vertex V3 to the graph. So I have to call this routine three times. If I call, then I'll get vertex V1 and V2 and V3. So this is adding the vertices. Now we'll add the edges. I'll be adding edge V1 and V2 to the graph. I'll be adding V2 three vertices to the graph G. The same way can add vertices from V3 to V1 to the graph G. So this is the process of inserting the edge. I can add one more edge or one more vertex. I can insert. So suppose this is V4. I can add the vertices. I can add even edge also. So these two helps me to insert vertex and edge. Suppose you don't want any edge, you can remove that delete vertex. In the same way, you can delete edge also. This routine is to check whether the graph is empty or not. Then we have got one more terminology called adjacency list or adjacency matrix. We can create that with the help of adjacent. So with this, I'll be ending this presentation. Thank you for listening.